in case you don't know, I'm Victor. I'm the TA. Here are the 4 chapters you're going to be tested on. Chapter 3 is torsion. 4 and 5 are bending. Chapter 5 is just harder bending questions. That's kind of how I saw it. And then 6 is shearing and beams. I'm going to mostly go over 3, 4, and 5 today because 1, you guys just got killed on the exam, so I need to spend a lot of time going over that. And 2, I don't really know Chapter 6 that well, so I'm going to let Dr. Supaska cover it during class. So, sorry. I'll go over a little bit. I'll tell you what I know, but that's up to you guys to figure out. On the right-hand side, it's a basic, if Victor's your TA, this is how you get points rubric. All right? I'll tell you right now, step 1, 3-body diagram. Okay? It's like writing your name, but even then, a couple of you have been forgetting to write your names on homework and quizzes, so it makes me kind of nervous. Draw a 3-body diagram. Step 2, write down what you know and what you don't know. Okay? Writing what you know, simple things, I'll give you points for that too. You know? Write down what you don't know because I'll help you with step 3. You have an equation sheet, you just have to find a way to connect the things you know and the thing you don't know, and plug and chug. Okay? Interesting story today. I was planning for this, and I was like, plug and chug, is that like an official term? And so I Googled it, and of course, Urban Dictionary pops up. And the first definition of plug and chug is pretty correct, right? It's an engineering term. You know, you find the equations and you plug it into your calculator. And then the other definitions were weird. They were disgusting weird. Like, I'm not allowed to talk about it, but if you want to look that up, that's up to you. All right. So this, you guys are welcome to leave whenever you want. Come back in whenever you want. Eat food. Just don't make a mess, otherwise I get in trouble. Here's the plan. I'm going to go through everything that I think is important. I'll probably throw a couple example problems, and then if you guys want more example problems, ask for more, okay? And then I'll stop in between, ask you guys if you have any questions. If you have any questions, feel free to ask questions. All right, let's do it. Chapter 3, torsion. Big time equations you need to know. Okay, the first part is solid cylindrical shafts. Okay, if you don't know what that looks like, you're in trouble. Switch to E or something. Okay, solid cylindrical shaft. X equals PC over J. For the most part, I'm going to cover things that are likely going to be on the test, but whatever I don't cover can also be on the test. So,
You haven't actually seen the test?
No, kind of. I discussed it with her because I was like, they got 61 on the quiz, and she's like, okay, we got to figure out a way to make this test a little easier. So we had that discussion, and then we kind of discussed what we'll go over, and I'm going to cover exactly what's going to be on the test and more, so you guys don't know what's on the test. I can't just tell you what's on the test. All right. I had a professor freshman year, greatest professor I ever had. Second year. Some guy asked the professor, "What's going to be on the test?" And he's like, "I hate that question. You know why? Because it's essentially asking me, how stupid can I be and pass the test?" Yeah, that's about right. We want you to learn as much as you can, so I can't tell you what's on the test. All right. Next, shear and torsion. Torque times the distance, the furthest distance from the center to the outside, okay? So, if here's your center, it's not here, it's not here, it's not here, okay? It's right on the edge. J, this is the inertia, but it is J because the inertia is calculated going this way. That's the axis you're rotating on. For a solid cylindrical shaft, J equals pi over 2, C to the 4th. Notice if you were lazy, you could just cancel out the C's. I guess that would be okay in the exam. Next thing, angle of twist. TL over Okay, J is the same. L is the length. This is L. Okay. Torque's the same. And G is a material property. It's something modulus. I don't know what it is. Some name. Okay, I'll tell you this right now. This number is usually pretty small, especially in radians, okay? If you have like a steel shaft, it takes a lot to twist it. That doesn't mean she won't give you a problem where you'll get, a shaft's this big and it twists 100 times, okay? If she gives you those numbers, she gives you those numbers. All right, just like what happened in the first exam when you get the safety factors less than 1. Okay, just be cautious. If you think this number is way off, just make a little note. It's fine. Maybe she'll decide to give extra credit or something. Remember, this is in radians, not in degrees. I would check your calculators. What else do I have to say? If she asks for angle of twists per unit length, that is simply erasing the L and putting it here. Okay, so it would just be T over JG. That's all it'd be if she asked for the angle of twist per unit length. So the units for that would be radians per meter. Okay? Don't mess that up. I have an example problem. We'll do it later. All right. Next thing. Hollow shaft. It's not too different. Okay? Everything's the same, essentially for the J. Okay, remember, C is the distance from the center to the furthest point from the center on the piece. Okay? So it's still going to be here. C is going to be the same value on these parts. Okay? So don't confuse that. If they give you the outer radius or the inner radius, it's always the outer radius. Okay? Also, if they give you the outer diameter, you have to divide it in half. Okay? I know. There's this one kid on the first exam. The question was like, if the length of the bar was 6 feet, da-da-da-da-da. And he's like, why? Why'd you tell us 6 feet? Because it's so hard to convert it to inches. And I was like, this guy's crazy. So I wrote on his paper, why not? It's an easy step. Come on, guys. But don't forget. All right? So, TC. I will put a little subscript outer just so you guys remember. And then J, okay? The J is where most people mess up, okay? They usually get confused between C outer to the 4th minus C inner to the 4th, or C outer minus C inner to the 4th. And they're like, I don't know which one it is, so it's a coin flip, and they usually pick the wrong one. So, I'm just going to quickly explain to you why it's this one and not this one. So essentially what you're doing for the J value, you're doing J equals J of the whole outer piece as if it were a solid shaft, minus J of the inner piece, pi over 2, C outer to the 4th, minus pi over 2, C inner to the 4th, and then you're just simply factoring it. That is about the only thing that changes with the hollow shaft. Okay, next thing, square shaft, or rectangle. A, B, okay. The equations are similar, but not really. T over C1 AB squared TL C2 AB to the 3rd G. Okay, If you look at the equations, they're kind of similar. Looking at the solid shaft, you got T's, you got a C just on the bottom, and then you have a J equivalent for your. Did you have a question?
Yeah, what does it say as in D over C what?
D.
T over C.
Oh, T over C1, subscript 1. A, B squared. Yeah, I need to write bigger. And then TL, C2, C subscript 2, A, B to the third times G. Okay? C1 and C2 are properties of the shape. Okay? You have to look at your rectangles, cross section, find out what A and B is. They usually tell you. You look at this table that tells you, okay, if the A-B ratio is 1.738, then C1 and C2 equals these specific values, and then you just plug those in. Yeah.
Are you guys gonna give us like the tables or?
If you have a square cross section, we'll give you the tables. This thing, okay. This dimension is 4. This dimension is 2, and on the inside, this is 3.5, and this is 1.5. Okay. Capital A is. The third quiz is just like, if you guys don't have paper, I'll cancel the quiz. I was like, who doesn't have paper? I just, yeah, I don't have paper, yeah. I don't know how many friends in the class either that have paper. I'll tell you, I did not have any engineering friends in college. I just had sports friends. And my blow-up doll. Alright, enough of that. Okay. It was a birthday gift, okay?
Yeah.
I pulled this equation from the book. Dr. Zupanska has another equation that I totally forgot in her slides. That was the answer to quiz 3. The ds is essentially the perimeter. Okay, so it'd just be 4 plus 2 times 2. Okay. So those are the main.
Do you want her other equation?
What?
Do you want her other equation?
Sure.
So theta equals tau s over 2a
Tau s over 2
capital A.
capital A G. That's the other equation. When you use one over the other, it's probably this one, because I've never seen this one used. So hint, this is probably not going to be on the exam. Not going to be on the exam. Probably not. Probably not. I said probably not. And one more condition. Elastic. What does elastoplastic mean? It's part elastic and part plastic. I don't know how much easier I could put it. Okay, I had a picture. I was thinking that it was going to be like a chem class where you have whiteboards and then a projector on the side, so I made a little PowerPoint thing. But I have a picture of Jolly Ranchers that are hard on the outside and chewy on the inside. That's what this is. Okay? It's soft on the inside, hard on the outside. That's all it is. So the cross section will look like this, and that shaded part will be gooey. That's the plastic portion. Okay? Equations you need to know. That's a row, not whatever you think it is. Third.
Is that C cubed?
What?
Is that C cubed?
C cubed. C cubed, rho y cubed. Okay? Rho y. I shouldn't have colored the inside. I'll draw a bigger hat. Okay. The radius of the gooey stuff is rho y. The radius of the outside is c. Okay? If they give you c and the thickness of the hard stuff, the gooey stuff is c minus the thickness. Okay, remember, it's not diameter minus the thickness. It would have to be the diameter minus 2 thickness for it to be equivalent. Alright, so this is most of the portion, but we're going to apply it to more complicated problems. Okay?
Wait, so is the inside part rho y or is it t?
Rho y.
Okay.
Yeah. Okay. Ty is calculating t as if it was like normal. So if this equals j, nope, this equals tc over j, then ty, this is the ty equals right? Tau j over, where'd it go? Just go. Over c. All right. This is, okay, I would bet 3 chickens and a goat that you wouldn't have a problem on an exam like this. This is too easy. This is freshman year kind of stuff, okay? This is basic. What you're probably going to get is something more like this, and then this is going the other way. Okay? You got different diameters, and you're going to have different moments throughout the thing. So, believe it or not, free body diagrams are not just an image with all the external forces. It's an image with all the external moments as well. Okay? That's what killed most of you guys on this last quiz. We'll go over it more in depth later, but you guys would, if you remember the problem, it looks something like this, right? You guys would draw it, and you guys would get the reaction force right. You guys would draw this, and then that's it, and then you just get totally screwed. So, because it's a wall, there's also a moment that can be applied if necessary. Okay? That was actually the first thing I was going to cover. Basic statics. Okay? Let's see. If your beam is on rollers, what possible reaction forces or moments can be applied? Fy, that's it. Okay? You can't apply a force to the side. If you have a pin, okay, you can apply both Fy and Fx. Okay? And if you have a wall, you can apply Fy, Fx, and the moments. Okay? You can't forget the moment. When we get to shear and bending diagrams, you're going to get screwed really, really bad if you don't have the moment. Okay? But, back to this. Okay, so what would your free body diagram kind of look like? Okay, I'll let you draw it as one straight line even though the diameters are different. Okay, this is all you have to do. This, we'll call this MA, MB, it's going the other way, and then moment reaction. Okay, because you know for sure there's going to be a moment reaction unless these two are equal. Okay, you can't forget that. Going back into looking at this and seeing what parts feel what moments, Let's just assume this moment is at the very tip of this, and then this moment is at where they intersect. Okay? If you draw the free body diagrams for the individual pieces, you'll get MA. Let's ignore the MB for now, and then a reaction. Reaction, B reaction. Okay? They're going to be equal and opposite. So the torque or the moment in this part is equal to MA. Okay? The other side, you got MBR, and then going in the other direction at the same spot, you have MB, and then you have the moment reaction at the wall. Okay? So this portion will be equal to, since these are opposite directions, let's say they're opposite direction, it would be MBR minus MB. Okay? And then this portion would be equivalent to that number, which is also the same thing as the reaction at the wall. Okay, I'm going to write that down. Moment and beam BC, or whatever, equals R minus MB. I'm gonna erase this. Anybody need it? Okay, let's do that. When you guys see a problem that looks something like this, and then let's just say it's a wall. Okay, and then they say, okay, there's an applied moment at this wheel, there's an applied moment at this wheel. Yeah.
Can you push the other board up?
Wait, how do you expect me to write on it?
No, the one behind.
Oh, this one you can't. I don't think you can. I have
Should I
a solution
delete this
for your
part?
problem. I think being a TA gives me free health insurance on campus or something. So let's hope they have it. Okay. This is the same thing as.
Wait.
Okay. So when you see those wheels, don't freak out. Another thing, you can have a problem that's like, you can have another problem that's like, okay, instead of a wall here, you have a motor. Okay, they will tell you what the motor is applying for the most part. If not, then you just have to solve for it if there's no wall on this side. But usually they tell you there's a motor, and then on this side there'll be a wall. Okay, so free body diagram for that will look like reaction of the wall, whatever this is, whatever that is, and the moment of the motor. That's weird. And then they'll give you this, they'll give you these two, and then you just have to find the reaction of the wall. Okay, the motor is just another applied moment. Okay, the last thing that usually gets people the most. Is everybody done with this? I don't want to stand on the chair. The bottom part? Okay, when you have a problem like this, okay, angle of deflection. So it's A, B, C. Okay. You want to find, not deflection, the angle of twist. You want to find how much the point A is twisting. Okay. It's pretty simple. The angle of twist of A equals twist of shaft AB plus the twist of angle BC. Okay, so you kind of have to get into the mindset of why it is this equation, okay? You have to think to yourself, all right, I want to know how much point A is twisting, okay? I can calculate for this piece, from A to B, how much is twisting, but I don't know how much B is twisting. So how much is B is twisting? I can calculate this piece from B to C, how much that twists, okay? And then you know C doesn't move because it's attached to a wall, okay? That's what I wrote here. Find your zeros or solving condition, okay? You would, if you had, a million of these, you would just keep going until you ran into a wall, because that wall is your zero condition. That's kind of how you solve the problem. So once you have the wall, you work backwards. You find how much this twists, and then from there you find out how much this twists, and you add it together. Okay? So the big thing is, people get terrified when they see this, and then one thing changes. Do you know what kind of problem that is? That's a gear problem. Okay, they're like, oh, I don't know what to do. Where do I start? That's my favorite thing to ask people when they come in for TA help. They're like, all right, so what do you need help on this problem? He's like, I don't know where to start. Come on, you gotta know something. All right, so you draw your free body diagram, step one. What you know, they'll give you the gear sizes. They'll give you the diameter of the shaft. Okay, what you don't know how much this A part twists, how much this B part twists, how much the C part twists. Okay, but your solving condition is this D. I didn't say that. Okay, you know anything attached to the wall doesn't move. Okay, so when you go back and you visualize it, okay, from here I can see how much C twists because I can calculate C to D. And then you use your gear ratios and you find how much B turns. And then from there, you can find how A turns, okay? I'm going to write down the gear ratios for you because you guys get confused. And I'll explain to you why, so it's easier to remember, okay? They're not the same. The torque of A, or no, let's write the torque of B times the radius of C equals the torque of C times the radius of B. Okay? And you may ask, this is why. Or why is this? Okay? And you have two gears pushing on each other. They push at this point. A certain force. Okay? Newton's third law, equal and opposite. Okay, so force B equals force C. If you recall, torque is equal to force times the radius. So that means the force is equal to torque over R. So if you plug those into here, torque B over radius B equals torque C over radius C, and then you get this, okay? So you got to remember for torques, different letters on the same side. Okay? The other gear ratio you need to know is B equals CRC. Okay? These are on the same side. When you visualize it, the gears' teeth interlock. Okay? When one gear moves 3 teeth down, the other gear has to move 3 teeth up. That's how gears work. So the amount of distance on the perimeter traveled of the gears are the same. That circumference is equal to the angle times the radius. What's the word? What's the terminology for that small portion of a circle? Arc length. Okay. The arc lengths, the values of the arc lengths are the same when two gears are rubbing against each other. Okie dokie. All right. That's all I have for torsion. So I was thinking about it, I was like, should I go through and find an example problem? Nah. I'm gonna make a problem right now and we're all gonna solve it. And then that way you guys have to solve it to make sure I'm right, because I have no clue. Homework. What are the chances of her picking the exact same question? And then everybody here would get a perfect score on the question. Nah, see, I gotta make up the question.
Yeah, what's the problem with giving us the question on the exam?
All right. Well, boom. Why not, right? This will make it. We'll do metric units. This will be 100 mils. This will be 10 millimeters. This will be 50 millimeters. Wow, those numbers are so original. All right. Oh, 50. Okay. So these two are going in the same direction. This one's going in an opposite direction. 18. All right, I'll give you guys, I don't know, 5 minutes. I just want you to go through the motions, okay? Kind of draw the feedback diagram, figure out what equations you'll need, how you would solve it. Oh, I didn't even ask you the question. Where is Tmax? And let's do. Let's see. We'll give you guys like 5 minutes to kind of. And 0.3 meters. It's a nightmare. I switched units. I know. Meters and millimeters. Oh, yeah. Oh, we need G values too, huh?
Yeah, right.
60 gigapascals for everything. What's so funny?
Victor, can you write the 10 because it's showing like 0 here?
Just to add on to the thing about the torques, he was saying sometimes the homework, there is a right answer for positive, negative. That's because the problem or the picture itself tells you what's positive, what's negative. So that in that case, the positive and negative matters, right? If I said this is positive, okay, right hand rule, okay, this would be a positive torque, this would be a negative torque, and this would be a positive torque, or whatever. It's a two-dimensional picture. It's hard to tell which way they're actually turning. Okay, but if they don't have the axis, whatever you declare as positive, negative is positive, negative. Okie doke. All right, let's try to solve it real quick, so we can get to the good stuff. Bending and moment. Okay, whoever didn't write their name on the last quiz, you're the guy that drew the surfer dude that said cowabunga. So, on your moment diagram. That's literally the idea. Like. Moment fluid diagram. Away. And he put a little caption that said California. I was like, okay. All right. Free body diagrams. Reaction. You gotta put names. You can't just draw it. You're gonna have to put a name. So moment A, moment B, moment C, and then moments called reaction. Okay, you got 7, 5, 18.
I will try to sort it by like.
Okay, sum of moments equals 0.
I meant to just to Gmail because it's like this slide.
Okay, let's say this way is positive. So these two are positive and this middle one's negative. So 17 plus 18 is 25. That's convenient. Minus 5 is 20. But since you're bringing it to the other side of the equation, it's minus 25. Or minus 20. Kilonewton meters. Units. Okay, that's pretty easy. All right. Now you got to go through and see how much torque is in each piece. Okay, this first piece, you would have the 7, and then the reaction. Okay, yeah.
It should be positive because shouldn't it be minus MR since it's going in the same direction as MD?
Yeah. Okay, I drew it negative.
Yeah.
So it should be minus and minus.
So it would be minus MR, yeah. If I had drawn it the other way, it would have been negative. But just know it's in the same direction as this one. That's what it really matters. Okay, yes, you're right. But when you draw your free body diagram, you can draw this any direction you want. Right, so just remember which way it goes. Okay? You might have to put like clockwise or counterclockwise. Alright, so for A to B, you got the 7 kilonewton meters, and then you have the reaction, equal and opposite. So you know the torque going through this is 7. Okay? I'm not going to write out each equation. You should on the exam, but I'm not going to, because, yeah. Okay? The next one is 7 minus 5, so it's 2. Okay? These are in the same direction because the 7 is greater than the 5 in the other direction. Okay, the next piece is plus 18, so 20. And then that should be correct because at the wall you're going to hit another 20, and that'd be your 0. Alright, for tau max, tau for this one equals 7, remember it's kilonewton meters, times the C value, which would be half of that, 50 millimeters, and then put it in meters, so it's 0.05 meters over pi over 2. 0.05 to the 4th. Okay, the next one would be 2 times half of 10 is 5, and that's 5 millimeters. 2 times 1.5 and then the last piece would be 20 meters. 50 is 25. Right? Yep. 2. Oh, 25. Okay, you can solve the 3, and then you pick the biggest one, because that's what the question asks, tau max. Okay? I'm not going to go over every possible example, but they might ask you, you know, what's the max torque you can apply without exceeding this many pascals for shear stress. Okay, you would have to work backwards, solve the equation in a different way, so just be cautious of that. For the angle of twist, like I said, you know at the wall is 0. So you start from the left, twist, oh, you actually start at B, right? Yeah, twist the B. So twist the B equals twist of link BC plus CD. And because you know D is a wall, that's where you stop. Okay? Equations. Torque of B, torque of this, so let's do this. I'm just going to write the equation over here, TL over JG, okay? Torque of this portion, 2 times the length, 0.1, over the same J value, times the G, 60 times 10 to the 9th, okay? Remember, giga is 10 to the 9th, mega is 10 to the 6th, kilo is 10 to the 3rd, okay? That should be all you need to know, okay? Plus 20 times length, 0.3, 5 over 2, 4, 60 times 10 to the 9th. Okay? Remember, it's in radians. We'll probably take the answer in both. We will take the answer in both radians and degrees. Yeah. And that should be it. Any other questions? Any problems with this? Okay, remember, I can't cover every example. I'm not going to go over a gear problem. I'm not going to go over a hollow, but I gave you all the questions to solve from. Just remember, kind of follow those 4 steps. Free body diagram, write what you know, find the solving condition, plug and chug. Should be good. All right?